We are in chapter 6, where we are discussing transformation of stresses and strains, failure theories, and thin-walled pressure vessels. This is the fifth session in chapter 6 and the 47th session overall. Here we discuss transformation of strains in two dimensions. This is a block diagram of sessions covered in the first four chapters. The fifth chapter was on shear, and the sixth chapter, among other discussions, includes transformation of stresses and strains. We have covered 4 sessions in transformation of stresses, and this is the first session involving transformation of strains. Here we develop formulas and discuss Mohr circles, transformation of strain in 2 dimensions. Earlier we discussed transformation of stresses. Here we have a beam subjected to a load. The element shown here is 3-dimensional. However, there is no normal or shear stress acting associated with the z direction. Hence, most of our analysis can be carried out by considering a 2-dimensional element as shown. These are the stresses that will normally act on the element. As the element is rotated, the stresses will vary. We earlier developed equations of variation of the stresses with angle. This element subjected to stresses will undergo strains. As the element is rotated and different stresses act on the element, the strains also will vary. So now we will study transformation of strains. Consider O as the reference point, and we'll find out the strain of point A. We'll find out strains for each type of stress first. Here sigma x is tensile and the element will extend in the x direction as shown. If epsilon x is the strain in the x direction, then the extension here will be epsilon x dx. Here the strain due to sigma y is shown. If epsilon y is a strain in the y direction, then the extension will be epsilon y into dy as shown. A here shifts to A1, and in this diagram A shifts to A2. The corners of this element are right angles, so the corner at O is a right angle. One can physically see that due to the shear stresses acting on the element will distort in this manner. So the angle at O will no longer be a right angle. It will reduce by alpha plus beta. So the shear strain is the change in angle and equal to alpha plus beta. In this diagram, we have rotated the element, so the change in angle is shown on one side. The change in length will be gamma xy dy. So the point A due to shear has moved to A3. We'll now consider the strains at point A due to the 3 types of stresses together. So in this figure, due to sigma x, the strain is epsilon x dx. Due to sigma y, the strain is epsilon y dy, and due to shear stress, the strain is gamma xy dy. So considering all the strains, the final position of the point A is A dash. Here we consider strain of the point B. The reference point O is taken as this point. Due to sigma x, the strain is epsilon x dx. Due to sigma y, the strain is epsilon y dy. Due to the shear stresses acting, element distorts as shown here. Element is rotated and the shear strains are shown by one angle in this diagram. The point P moves by gamma xy ey due to shear stresses. In this diagram, the strain of point B due to the three different types of stresses are shown. So due to sigma x, the point B moves towards the left by epsilon x dx. Due to sigma y, there's a vertical extension of epsilon y dy. Due to the shear stress, there's a movement towards the right of gamma xy dy. You can see that the strain of point B is different to the strain of point A we discussed earlier. This is a magnified diagram of the strain of point A. So A has moved to A dash as was discussed earlier. We consider the length of OA to be dx dash. The direction of OA is considered the x dash direction. We'll find out the normal strain of point A. Our normal strain is increase in length over original length. Now OA is the original length and the increase in length is given by these three blue lines. So the increase in length is AB plus CD plus EA dash. This angle is taken as theta. So BAC is also theta. BCF is theta. So FCB is 90 minus theta, which means CFD is theta. Also FA dash E is theta. These three lengths in black are A1, A2 and A3. So the increase in length of OA, which is given by epsilon x dash dx dash, is equal to A1 cos theta plus A2 sin theta plus A3 cos theta. So these three are these three blue lines. We earlier found out A1 is epsilon x dx, A2 is epsilon y dy, and A3 is gamma xy dy. Now dividing this equation by dx dash, we get this expression. Now dx divided by dx dash is cos theta. dy divided by dx dash is sin theta. Substituting the values, we get this expression. Using 2 sin theta cos theta as sin 2 theta, we get epsilon x dash is equal to epsilon x cos square theta plus epsilon y sin square theta plus comma xy divided by 2 sine 2 theta. We can write cos square theta and sine square theta in terms of cos 2 theta. Substituting, we get the expression epsilon x dash is epsilon x plus epsilon y divided by 2 plus epsilon x minus epsilon y divided by 2 cos 2 theta plus comma xy divided by 2 sine 2 theta. This equation of transformation of strain involving epsilon x dash is similar to form of the expression of transformation of stress involving sigma x dash. So replacing epsilon x dash by sigma x dash and epsilon x and y by sigma x and y and comma xy divided by 2 by tau xy will get the equation of transformation of stress. Earlier we found out the normal strain of OA. So it was in the direction of OA. In order to find shear strain, we need to find out this angle alpha, for which we need to find out the distance L perpendicular to the direction of OA. Now L is given by these blue lines. So L is equal to dF minus FE minus BC. The black lines give A1, A2 and A3. We can write these three dimensions in terms of A2, A1 and A3. We earlier determined these angles as theta. So dF is A2 cos theta. FE is A3 sin theta, which we have given here. And BC is A1 sin theta, which we have written here. Now A2 is epsilon y dy, A1 is epsilon x dx, and A3 is comma xy dy. Now from this triangle, L can be written as tan alpha dx dash. Now alpha being small, we can write tan alpha dx dash as alpha dx dash. Now dividing by dx dash on both sides, we get this expression. As earlier, dx divided by dx dash is cos theta and dy divided by dx dash is sin theta, which we substitute in this expression. So we get alpha in terms of epsilon x, epsilon y, and comma xy and theta. We earlier considered a point P to the left of the reference point O. We found out how the point B moved due to the stresses acting on the element. It finally attained the position B dash. Here the diagram is magnified, and we have also considered OP to be perpendicular to OA. The length of OA was considered to be dx dash, so the length of OP is considered as dy dash. The direction of OP is considered to be the y dash direction. This angle is considered as theta dash. Then, as earlier, CPD would be theta dash, EFD be theta dash, and also GP dash F would be theta dash. We'll find out the normal strain of OP, which would be the increase in length of OP divided by the original length. As earlier, the increase in length of OP would be given by these three blue lines. We know P1, P2, and P3, which is given in black. We then have the increase in length epsilon y dash b y dash as BC, which is B1 cos theta dash, plus BE, which is B2 sin theta dash, minus G D dash, which is B3 cos theta dash. Now B1 is epsilon x dx, B2 is epsilon y dy, and B3 is gamma xy dy. Dividing both sides by dy dash, we get this expression. Now, as earlier, dx divided by dy dash is cos theta dash, and dy divided by dy dash is sin theta dash. So we get epsilon y dash in terms of theta dash. We can find epsilon y dash in terms of theta. Now theta dash is equal to 180 minus bracket 90 plus theta. So theta dash is 90 minus theta. Then cos theta dash is equal to sin theta, and sin theta dash is equal to cos theta. And cos square theta dash becomes sin square theta, and vice versa. We write this expression in terms of trigonometric functions of 2 theta. So we get epsilon y dash is equal to epsilon x plus epsilon y divided by 2 minus epsilon x minus epsilon y divided by 2 cos 2 theta minus gamma xy divided by 2 sin 2 theta. Again, this equation is in the same form of the expression of sigma y dash. In order to find shear strain, we need to find beta, for which we need to find L dash. To find L dash, we need to know the length of these blue lines. So L dash is equal to EF plus GF minus CD. We earlier obtained B1, B2, and B3, is shown by the black lines. EF is B2 cos theta dash. GF is B3 sin theta dash. And CD is B1 sin theta dash. So we get this expression. Now B2 is epsilon y dy. B1 is epsilon x dx. B3 is gamma xy dy. L dash is equal to tan beta dy dash, or beta dy dash. Dividing both sides by dy dash, we get this expression for beta. Substituting dx by dy dash as cos theta dash and dy by dy dash as sin theta dash, we get this expression. We earlier saw that theta dash is equal to 90 minus theta, and cos theta dash is equal to sin theta, and sin theta dash is equal to cos theta. Substituting, we get this expression of beta in terms of theta. We earlier found this expression of alpha. Gamma x dash y dash is equal to alpha plus beta. So we add these two expressions. We get minus bracket epsilon x minus epsilon y 2 sine theta cos theta, which we write as sine 2 theta, plus gamma xy cos square theta minus sine square theta, which we write as cos 2 theta. So this is the expression of shear strain. Here we'll be discussing Mohs circle for plane strain. The treatment is quite similar to Mohs circle for plane stress. We earlier obtained algebraic equations for epsilon x dash and gamma x dash y dash. If we move the first term to the other side, we get equation 1. We divide all terms in this equation by 2 to get equation 2. We then square both sides of equation 1 and 2 and add them up. Then, as earlier, we get this expression. Here, epsilon x dash and gamma x dash y dash divided by 2 are unknowns. Epsilon x, epsilon y, and gamma xy are knowns. This equation can be written in the form of x minus a square plus y square is equal to r squared, where x is epsilon x dash, y is gamma x dash y dash divided by 2. A is epsilon x plus epsilon y divided by 2. And r is the square root of this term on the right. This is the equation we obtained for Mohs circle of stress. So in the Mohs circle of stress, if we replace sigma x dash by epsilon x dash, tau x dash y dash by gamma x dash y dash divided by 2, and sigma x, sigma y, tau xy by epsilon x, epsilon y, and gamma xy divided by 2, then we'll get this equation, which is for plane strain. One needs to remember that tau xy gets replaced by gamma xy divided by 2. Let us now look at the sign conventions used. If there's an increase in length of a side of an element, then the normal strain is considered positive. If there's a decrease in length of a side of an element, then the normal strain is considered as negative. Earlier when discussing angles, formulation, we mentioned that if this right angle gets reduced, as is the case here, then the strain is considered positive. If the right angle increases in size, then the strain is considered as negative. When it comes to plane strain, we are dealing with sides. The sides EF and DC have rotated clockwise, and they are considered to be associated with negative strain. The sides DE and CF has rotated anti-clockwise, and they are considered to be associated with positive strain. Earlier we discussed convention for shear stress for Mohs circle. So in this element, the shear stress in DC and FE are considered to be negative, and the shear stress in FC and ED are considered to be positive. So our shear stress convention matches with our shear strain convention. The Mohs circle for plane strain is developed in the same way as the Mohs circle for plane stress. Thus, first we plot 2 points on the opposite ends of a diameter. Consider an element subjected to stresses as shown. Let this be the deformed element. In figure C, this element has been rotated slightly and the strains are shown. The shear strain is shown on one side. Consider the side CT. The normal strain is epsilon x, and since CD rotates clockwise, the shear strain is minus comma xy divided by 2. It is plotted as point A. Considered CF. The normal strain is epsilon y, and since CF rotates anti-clockwise, the shear strain is comma xy divided by 2. It is plotted as point B. So AB gives the diameter, as in the case of Mohs circle of plane stress. Half of the summation of the normal stress, epsilon x and epsilon y, gives the center. This means that the sum of the normal strain of the opposite sides of the diameter will be always equal. This is again similar to the plane stress case. So here epsilon max plus epsilon minimum is equal to epsilon x plus epsilon y. Here in figure 3, we have plotted A, B and formed the whole Mohs circle. We have considered this as the initial stressed element. The same element with the same stresses is shown here. Now, if the element is rotated, then all the stresses acting on the element will change. In general, consider that this element has been rotated by theta 1 degrees counterclockwise. Since the stresses acting on this element are all different, the strains also will all be different. Here again the distorted element is shown. In this figure we have rotated this element slightly so that the shear strain is shown on one side, and we have shown all the normal strains and the shear strain. If we want to know the shear strain and the normal strain of this element, then we can use the Mohs circle for plane strain. Here the rotation was theta 1 in the counterclockwise direction. So from OA we have rotated to theta 1 in the counterclockwise direction and reached A dash. We can extend A dash O to B dash. Then A dash B dash will give the strains associated with this element. If this element had rotated in the clockwise direction, say by theta 2, then in the Mohs circle we'll have to rotate by 2 theta 2 to get A double dash. Then A double dash B double dash will give the strains of the rotated element. Here we discuss the principal strain plane and the magnitude of the principal strains, and the plane of maximum and minimum shear strain and the magnitude of maximum and minimum shear strain. The direction of the principal strain coincide with the direction of the principal stresses. We earlier saw that the equation of transformation of strain are quite similar to the equation of transformation of stress. We found the equations of direction and magnitude of the principal stresses from the equation of transformation of stresses. In a similar manner, the equation of direction and magnitude of principal strain can be found from the equation of transformation of strain. However, the method is nearly identical to that of principal stresses and as such is not repeated here. This is the equation of direction and these are the equations of magnitude of principal stresses. In these equations, we replace tau xy by gamma xy divided by 2 and sigma x and sigma y by epsilon x and epsilon y, and then we get the equation of direction of principal strain and the equations of the magnitude of the principal strain. Also, the equations of direction of maximum and minimum shear stress and magnitude of maximum and minimum shear stress are obtained from the equations of transformation of stress. The equation of transformation of strain being similar, the equation of direction and magnitude of maximum and minimum shear strain is similar to that of stress. Again, we do not repeat the derivation here. For stress, this is the equation for direction and this is the equation for magnitude. Substituting gamma xy divided by 2 for tau xy and epsilon x and epsilon y for sigma x and sigma y, we get these equations. Let's now discuss the direction and magnitude of the principal strains and the maximum and minimum shear strains in terms of the Mohs circle. We earlier took this element and rotated the element and schematically developed the Mohs circle of strain. The strain on the right face was plotted as point A and the strain on the top face was plotted as point B. With the diameter known, we can form the Mohs circle of strain. For this schematic case, if we rotate OA by 2 theta dash 1, we reach the plane of maximum principal strain. And if we rotate by 2 theta double dash 1 in the clockwise direction, we reach the plane corresponding to the minimum shear strain. This again is similar to Mohs circle of stress. This equation will give two values of theta dash. Half of this angle gives theta dash 1 and half of this angle will give theta dash 2. Also, this equation will give two values of theta double dash. Half of this value will give one of the values and half of this angle will give the other theta double dash.